In this chapter, our goal is to introduce some metrics for measuring the performance of a circuit and then investigate ways to improve that performance. We'll start by putting aside circuits for a moment and look at an everyday example that will help us understand the proposed performance metrics. Laundry is a processing task we all have to face at some point. The input to our laundry system is some number of loads of dirty laundry, and the output is the same loads, but washed, dried, and folded. There are two system components: a washer that washes a load of laundry in 30 minutes, and a dryer that dries a load in 60 minutes. You may be used to laundry system components with different propagation delays, but let's go with these delays for our example. Our laundry follows a simple path through the system. Each load is first washed in the washer and afterwards moved to the dryer for drying. There can, of course, be delays between the steps of loading the washer, or moving wet wash loads to the dryer, or in taking dried loads out of the dryer. Let's assume we move the laundry through the system as fast as possible, moving loads to the next processing step as soon as we can. Most of us wait to do laundry until we've accumulated several loads. That turns out to be a good strategy. Let's see why. To process a single load of laundry, we first run it through the washer, which takes 30 minutes. Then we run it through the dryer, which takes 60 minutes. So the total amount of time from system input to system output is 90 minutes. If this were a combinational logic circuit, we'd say the circuit's propagation delay is 90 minutes from valid inputs to valid outputs. Okay, that's the performance analysis for a single load of laundry. Now let's think about doing n loads of laundry. Here at MIT, we like to make gentle fun of our colleagues at the prestigious institution just up the river from us. So here's how we imagine they do n loads of laundry at Harvard. They follow the combinational recipe of supplying new system inputs after the system generates the correct output from the previous set of inputs. So in step 1, the first load is washed, and in step 2, the first load is dried, taking a total of 90 minutes. Once those steps are complete, Harvard students move on to step 3, starting the processing of the second load of laundry, and so on. The total time for the system to process n laundry loads is just n times the time it takes to process a single load. So the total time is n times 90 minutes. Of course, we're being silly here. Harvard students don't actually do laundry. Mummy sends the family butler over on Wednesday mornings to collect their dirty loads and return them starched and pressed in time for afternoon tea. But I hope you're seeing the analogy we're making between the Harvard approach to laundry and combinational circuits. We can all see that the washer is sitting idle while the dryer is running, and that inefficiency has a cost in terms of the rate at which n loads of laundry can move through the system. As engineering students here in 6004, we see that it makes sense to overlap washing and drying. So in step 1, we wash the first load, and in step 2, we dry the first load as before, but in addition, we start washing the second load of laundry. We have to allocate 60 minutes for step 2 in order to give the dryer time to finish. There's a slight inefficiency in that the washer finishes its work early, but with only one dryer, it's the dryer that determines how quickly laundry moves through the system. Systems that overlap the processing of a sequence of inputs are called pipeline systems, and each of the processing steps is called a stage of the pipeline. The rate at which inputs move through the pipeline is determined by the slowest pipeline stage. Our laundry system is a 2-stage pipeline with a 60-minute processing time for each stage. We repeat the overlapped wash-dry step until all n loads of laundry have been processed. We're starting a new washer load every 60 minutes and getting a new load of dried laundry from the dryer every 60 minutes. In other words, the effective processing rate of our overlapped laundry system is 1 load every 60 minutes. So once the process is underway, n loads of laundry takes n times 60 minutes. And a particular load of laundry, which requires 2 stages of processing time, takes 120 minutes. The timing for the first load of laundry is a little different since the timing of step 1 can be shorter with no dryer to wait for. But in the performance analysis of pipeline systems, we're interested in the steady state where we're assuming that we have an infinite supply of inputs. We see that there are 2 interesting performance metrics. The first is the latency of the system, the time it takes the system to process a particular input. In the Harvard laundry system, it takes 90 minutes to wash Okay, now let's apply all this analysis to improving the performance of our circuits. The latency of a combinational logic circuit is simply its propagation delay, TPD. And the throughput is just 1 over TPD, since we start processing the next input only after finishing the computation on the current input. Consider a combinational system with 3 components, F, G, and H, where F and G work in parallel to produce the inputs to H. Using this timing diagram, we can follow the processing of a particular input value x. Sometime after x is valid and stable, F and G modules produce their outputs, f of x and g of x. Now that the inputs to H are valid and stable, the H module will produce the system output p of x after a delay set by the propagation delay of H. The total elapsed time from valid input to valid output is determined by the propagation delay of the component modules. Assuming we use those modules as is, we can't make any improvements on this latency. But what about the system's throughput? Observe that after producing their outputs, the F and G modules are sitting idle, just holding their output stable while H performs its computation. Can we figure out a way for F and G to get started processing the next input while still letting H do its job on the first input? In other words, can we divide the processing of the combinational circuit into 2 stages, where the first stage computes f of x and g of x, and the second stage computes h of x? If we can, then we can increase the throughput of the system. Mr. Blue's inspiration is to use registers to hold the values f of x and g of x for use by H, while the f and g modules start working on the next input value. To make our timing analysis a little easier, we'll assume that our pipelining registers have 0 propagation delay and setup time. The appropriate clock period for the sequential circuit is determined by the propagation delay of the slowest processing stage. In this example, the stage with F and G needs a clock period of at least 20 nanoseconds to work correctly, and the stage with H needs a clock period of 25 nanoseconds to work correctly. So the second stage is the slowest and sets the system clock period at 25 nanoseconds. This will be our general plan for increasing the throughput of combinational logic. We'll use registers to divide the processing into a sequence of stages, where the registers capture the outputs from one processing stage and hold them as inputs for the next processing stage. A particular input will progress through the system at the rate of 1 stage per clock cycle. In this example, there are 2 stages in the processing pipeline, and the clock period is 25 nanoseconds. So the latency of the pipeline system is 50 nanoseconds. In other words, the number of stages times the system's clock period. The latency of the pipeline system is a little longer than the latency of the unpipelined system. However, the pipeline system produces one output every clock period, or 25 nanoseconds. The pipeline system has considerably better throughput at the cost of a small increase in latency. Pipeline diagrams help us visualize the operation of a pipeline system. The rows of the pipeline diagram represent the pipeline stages, and the columns are successive clock cycles. At the beginning of clock cycle I, the input x sub I becomes stable and valid. Then, during clock cycle I, the F and G modules process that input, and at the end of the cycle, the results, f of x sub I and g of x sub I, are captured by the pipeline registers between the first and second stages. Then, in cycle I plus 1, H uses the captured values to do its share of the processing of x sub I. And, meanwhile, the F and G modules are working on x sub I plus 1. You can see that the processing for a particular input value moves diagonally through the diagram, 1 pipeline stage per clock cycle. At the end of cycle I plus 1, the output of H is captured by the final pipeline register and is available for use during cycle I plus 2. The total time elapsed between the arrival of an input and the availability of the output is 2 cycles. The processing continues cycle after cycle, producing a new output every clock cycle. Using the pipeline diagram, we can track how a particular input progresses through the system, or see what all the stages are doing in any particular cycle. We'll define a k-stage pipeline, or k-pipeline for short, as an acyclic circuit having exactly k registers on every path from input to output. An unpipelined combinational circuit is thus a 0-stage pipeline. Here's a failed attempt at pipelining a circuit. For what value of K is the circuit a K pipeline? Well, let's count the number of registers along each path from system inputs to system outputs. The top path through the A and C components has 2 registers, as does the bottom path through the B and C components. But the middle path through all 3 components has only 1 register. Oops! This is not a well-formed K pipeline. Why do we care? We care because this pipeline circuit does not compute the same answer as the original unpipelined circuit. The problem is that successive generations of inputs get mixed together during processing. For example, during cycle I+1, the B module is computing with the current value of the X input, but the previous value of the Y input. This can't happen with a well-formed K pipeline, so we need to develop a technique for pipelining a circuit that guarantees the result will be well-formed. Here's our strategy that will ensure if we add a pipeline register along one path from system inputs to system outputs, we will add pipeline registers along every path. Step 1 is to draw a contour line that crosses every output in the circuit and mark its endpoints as the terminal points for all the other contours we'll add. During Step 2, continue to draw contour lines between the 2 terminal points across the signal connections between modules. Make sure that every signal connection crosses the new contour line in the same direction. This means that system inputs will be on one side of the contour and system outputs will be on the other side. These contours demarcate pipeline stages. Place a pipeline register wherever a signal connection intersects the pipelining contours. Here we've marked the location of pipeline registers with large black dots. By drawing the contours from terminal point to terminal point, we guarantee that we cross every input-output path, thus ensuring our pipeline will be well formed. Now we can compute the system clock period by looking for the pipeline stage with the longest register-to-register or input-to-register propagation delay. With these contours and assuming ideal zero-delay pipeline registers, the system clock must have a period of 8 nanoseconds to accommodate the operation of the C module. This gives a system throughput of 1 output every 8 nanoseconds. Since we drew 3 contours, this is a 3 pipeline, and the system latency is 3 times 8 nanoseconds, or 24 nanoseconds total. Our usual goal in pipelining a circuit is to achieve maximum throughput using the fewest possible registers. So our strategy is to find the slowest system component, in our example the C component, and place pipeline registers on its inputs and outputs. So we drew contours that passed on either side of the C module. This sets the clock period at 8 nanoseconds, so we position the contour so that the longest path between any 2 pipeline registers is at most 8. There are often several choices for how to draw a contour while maintaining the same throughput and latency. For example, we could have included the E module in the same pipeline stage as the F module. Okay, let's review our pipelining strategy. First, we draw a contour across all the outputs. This creates a 1 pipeline, which, as you can see, will always have the same throughput and latency as the original combinational circuit. Then we draw our next contour, trying to isolate the slowest component in the system. This creates a 2 pipeline with a clock period of 2, and hence a throughput of 1/2, or double that of the 1 pipeline. We can add additional contours, but note that the 2 pipeline had the smallest possible clock period, so after that, additional contours add stages and hence increase the system's latency without increasing its throughput. Not illegal, just not a worthwhile investment in hardware. Note that the signal connection between the A and C module now has 2 back-to-back pipelining registers. Nothing wrong with that. It often happens when we pipeline a circuit where the input-output paths are of different lengths. So our pipelining strategy will be to pipeline implementations with increasing throughput, usually at the cost of increased latency. Sometimes we get lucky and the delays of each pipeline stage are perfectly balanced, in which case the latency will not increase. Note that a pipeline circuit will never have a smaller latency than the unpipelined circuit. Notice that once we've isolated the slowest component, we can't increase the throughput any further. How do we continue to improve? 6004 students work around the dryer bottleneck by finding a laundromat that has 2 dryers for every washer. Looking at the timeline, you can see the plan, which is divided into 30-minute steps. The washer is in use every step, producing a newly washed load every 30 minutes. Dryer usage is interleaved, where dryer number 1 is used to dry the odd-numbered loads, and dryer number 2 is used to dry the even-numbered loads. Once started, a dryer runs for a duration of 2 steps, a total of 60 minutes. Since the dryers run on a staggered schedule, the system as a whole produces a load of clean, dry laundry every 30 minutes. The steady-state throughput is 1 load of laundry every 30 minutes, and the latency for a particular load of laundry is 90 minutes. And now here's the take-home message from this example. Consider the operation of the 2-dryer system. Even though the component dryers themselves aren't pipelined, the 2-dryer interleaving system is acting like a 2-stage pipeline with a clock period of 30 minutes and a latency of 60 minutes. In other words, by interleaving the operation of 2 unpipelined components, we can achieve the effect of a 2-stage pipeline. Returning to the example of the previous section, we couldn't improve the throughput of our pipeline system past 1/8 nanoseconds because the minimum clock period was set by the 8 nanosecond latency of the C module. To improve the throughput further, we either need to find a pipeline version of the C component or use an interleaving strategy to achieve the effect of a 2-stage pipeline using 2 instances of the unpipelined C component. Let's try that. Here's a circuit for a general-purpose 2-way interleaver, using, in this case, 2 copies of the unpipelined C component, C0 and C1. The input for each C component comes from a D latch, which has the job of capturing and holding the input value. There's also a multiplexer to select which C component output will be captured by the output register. In the lower left-hand corner of the circuit is a very simple 2-state FSM with 1 state bit. The next state logic is a single inverter, which causes the state to alternate between 0 and 1 on successive clock cycles. This timing diagram shows how the state bit changes right after each rising clock edge. To help us understand the circuit, we'll look at some signal waveforms to illustrate its operation. To start, here are the waveforms for the clock signal and our FSM state bit from the previous slide. A new X input arrives from the previous stage just after the rising edge of the clock. Next, let's follow the operation of the C0 component. Its input latch is open when FSMQ is low, so the newly arriving X1 input passes through the latch, and C0 can begin its computation, producing its result at the end of clock cycle number 2. Note that the C0 input latch closes at the beginning of the second clock cycle, holding the X1 input value stable even though the X input is starting to change. The effect is that C0 has a valid and stable input for the better part of 2 clock cycles, giving it enough time to compute its result. The C1 waveforms are similar, just shifted by 1 clock cycle. C1's input latch is open when FSMQ is high, so the newly arriving X2 input passes through the latch, and C1 can begin its computation, producing its result at the end of clock cycle number 3. Now, let's check the output of the multiplexer. When FSMQ is high, it selects the value from C0, and when FSMQ is low, it selects the value from C1. We can see that happening in the waveform shown. Finally, at the rising edge of the clock, the output register captures the value on its input and holds it stable for the remainder of the clock cycle. The behavior of the interleaving circuit is like a 2-stage pipeline. The input value arriving in cycle I is processed over 2 clock cycles, and the result becomes available on cycle I plus 2. What about the clock period for the interleaving system? Well, there is some time lost to the propagation delays of the upstream pipeline register that supplies the X input, the internal latches and multiplexer, and the setup time of the output register. So the clock cycle has to be just a little bit longer than half of the propagation delay of the C module. We can treat the interleaving circuit as a 2-stage pipeline, consuming an input every clock cycle and producing a result 2 cycles later. When incorporating an N-way interleaved component in our pipeline diagrams, We've been designing our processing pipelines to have all the stages operate in lockstep, choosing the clock period to accommodate the worst-case processing time over all the stages. This is what we'd call a synchronous, globally timed system. But what if there are data dependencies in the processing time? In other words, if for some data inputs, a particular processing stage might be able to produce its output in a shorter time. Can we design a system that could take advantage of that opportunity to increase throughput? One alternative is to continue to use a single system clock, but for each stage to signal when it's ready for a new input and when it has a new output ready for the next stage. It's fun to design a simple two-signal handshake protocol to reliably transfer data from one stage to the next. The upstream stage produces a signal called "Here's X" to indicate that it has new data for the downstream stage. And the downstream stage produces a signal called "Got X" to indicate when it is willing to consume data. It's a synchronous system, so the signal values are only examined on the rising edge of the clock. The handshake protocol works as follows. The upstream stage asserts "Here's X" if it will have a new output value available at the next rising edge of the clock. The downstream stage asserts "Got X" if it will grab the next output at the rising edge of the clock. Both stages look at the signals on the rising edge of the clock to decide what to do next. If both stages see that "Here's X" and "Got X" are asserted at the same clock edge, the handshake is complete and the data transfer happens at that clock edge. Either stage can delay a transfer if they're still working on producing the next output or consuming the previous input. It's possible, although considerably more difficult, to build a clock-free asynchronous self-timed system that uses a similar handshake protocol. The handshake involves 4 phases. In phase 1, when the upstream stage has a new output and "Got X" is deasserted, it asserts its "Here" signal and then waits to see the downstream stage's reply on the "Got X" signal. In phase 2, the downstream stage, seeing that "Here X" is asserted, asserts "Got X" when it has consumed the available input. In phase 3, the downstream stage waits to see "Here X" go low, indicating that the upstream stage has successfully received the "Got X" signal. In phase 4, once "Here X" is deasserted, the downstream stage deasserts "Got X", and the transfer handshake is ready to begin again. Note that the upstream stage waits until it sees "Got X" deasserted before starting the next handshake. The timing of the system is based on the transitions of the handshake signals, which can happen at any time the conditions required by the protocol are satisfied. No need for a global clock here. It's fun to think about how this self-timed protocol might work when there are multiple downstream modules, each with their own internal timing. In this example, A's output is consumed by both the B and C stages. We need a special circuit, shown as a yellow box in the diagram, to combine the "Got X" signals from the B and C stages and produce a summary signal for the A stage. Let's take a quick look at the timing diagram shown here. After A has asserted "Here's X", the circuit in the yellow box waits until both the B and the C stage have asserted their "Got X" signals before asserting "Got X" to the A stage. At this point, the A stage deasserts "Here's X", then the yellow box waits until both the B and C stages have deasserted their "Got X" signals before deasserting "Got X" to the A stage. Let's watch the system in action. When a signal is asserted, we'll show it in red, otherwise it's shown in black. A new value for the A stage arrives on A's data input, and the module supplying the value then asserts its "Here's X" signal to let A know that it has a new input. At some point later, A signals "Got X" back upstream to indicate that it has consumed the value. Then the upstream stage deasserts "Here's X", followed by A deasserting its "Got X" signal. This completes the transfer of the data to the A stage. When A is ready to send a new output to the B and C stages, it checks that its "Got X" signal is deasserted, which it is, so it asserts the new output value and signals "Here's X" to the yellow box, which forwards the signal to the downstream stages. B is ready to consume the new input and so asserts its "Got X" output. Note that C is still waiting for its second input and has yet to assert its "Got X" output. Let's summarize what we've learned about controlling pipeline systems. The most straightforward approach is to use a pipeline with a system clock chosen to accommodate the worst-case processing time. These systems are easy to design, but can't produce higher throughputs if the processing stages might run more quickly for some data values. We saw that we could use a simple handshake protocol to move data through the system. All communication still happens on the rising edge of the system clock, but the specific clock edge used to transfer data is determined by the stages themselves. It's tempting to wonder if we can adjust the global clock period to take advantage of data-dependent processing speedups. But the necessary timing generators can be very complicated in large systems. It's usually much easier to use local communication between modules to determine system timing than trying to figure out all the constraints at the system level. So this approach isn't usually a good one. But what about locally timed asynchronous systems like the example we just saw? Each generation of engineers has heard the siren call of asynchronous logic. Sadly, it usually proves too hard to produce a provably reliable design for a large system, say a modern computer. But there are special cases, such as the logic for integer division, where the data-dependent speedups make the extra work worthwhile. We characterize the performance of our systems by measuring their latency and throughput. For combinational circuits, the latency is simply the propagation delay of the circuit, and its throughput is just 1 over latency. We introduced a systematic strategy for designing k-pipelines, where there's a register on the outputs of each stage, and there are exactly k registers on every path from input to output. The period of the system clock, t-clock, is determined by the propagation delay of the slowest pipeline stage. The throughput of a pipeline system is 1 over t-clock, and its latency is just k times t-clock. Pipelining is the key to increasing the throughput of most high-performance digital systems.